Occasionally you come on something that just has too perfect of a name. This is the case with something called a lull chart. This is a tool that we're going to be using to track energy changes in a substance, but let's first give ourselves a situation to look at. So here's our situation. A piece of ice is placed on a hot skillet. So this is like on a stove or something. And what we're going to do is describe changes in energy. So it's pretty obvious what's going to happen here. As far as the kinetic energy of the atoms of the ice is concerned, those molecules are going to speed up. They're going to start moving more and more quickly. And if we're discussing this in terms of heat, we know that heat is going to flow from the hot skillet, from the high temperature, to the ice, the low temperature. And we can identify a couple situations here, and this part is really key. We're going to separate out places where the temperature changes and places where the temperature doesn't change. So let's look first. We have the ice warming up. So that is when we first throw it in there, the ice heats up, and that is going to cause increases in temperature. So we have this place where the temperature is increasing. I'm just going to say temp goes up. And then we have the ice melting. Here, the temperature does not change. So I'll say no change. And then we have, after the ice melts, we're going to have water heating up, or I'll say warming up. And here the temperature does change. So the temperature changes. And then after that, we're going to have the situation where the water boils if we leave it on long enough. So the water boils, and in this case, temp does not change. And this goes back to what you just read about phase changes, the fact that during a phase change, during melting or boiling, there is no change in temperature. So what's going to happen is we're going to build one of these lull charts for each one of these situations. And I'm just going to come down here and we'll do the first one. So the ice warming up. So this is our first lull chart. And to start a lull chart, what you do is write the letters LOL really darn big. So just like that. And what this is really going to be is this is going to be a chart describing what happens to our water. So inside the O, what we do is we write what's called our system. That is the objects that we're focusing on, that we're interested in the energy changes for. In this case, we're interested in the energy changes for the ice. And I'll call it H2O so that we don't have to worry about calling it ice or water or something different each time. So in that middle circle, I write the thing that I'm focused on, what I care about the energy for. So in this case, the H2O. And each one of these is going to turn into a graph. So this is our before graph, so our initial condition, and this is after. Now, when you work these problems for yourself, you don't necessarily have to write before or after. I will assume that this is the before condition and this is the after condition, but while we set it up, I want to make it clear what's going on. Also, for this part up here, where I divided it into times where the temperature is going up and where the temperature is not going up, you don't necessarily have to do that for each problem. I'm just doing that here to show you that we have these situations, and we'll have to do a different lull chart for each one of these situations. All right, back to these graphs. So the before graph, there are two things right now that we're going to be interested in, and we can add things to this graph later, and when you get into physics, we can use it for other things. But right now, there's two types of energy we're interested in. There's the energy associated with temperature, which we are going to, for lack of a better, call thermal energy. And so I'll say E sub TH. So that's the energy associated with the temperature. As temperature goes up, thermal energy goes up. As temperature goes down, thermal energy goes down. And I can also have what's called phase energy. And this is the energy associated with if it's a solid, liquid, or gas. And here's the way I want you to do this. For the before condition, with our temperature, we can make this whatever we want. We just have to be aware of whether or not the temperature is going to go up or down. In our case, we know the temperature is going to go up, and so I'm going to start this off, and this is completely arbitrary. You can pick how many ever you want. I'm going to put 2 blocks of thermal energy in there. Each one of these blocks doesn't necessarily represent a certain amount of energy. If you want to go that far, you can, but it doesn't have to. So I'm just saying I have 2 blocks of thermal energy. If the temperature goes down, I can take away one of those blocks. If the temperature goes up, I can add one of those blocks. All right, phase energy is the energy associated with whether it's a solid, liquid, or gas. And the way I want you to do this, 1 block will mean solid, 2 blocks will mean liquid, and 3 blocks we'll call a gas. And the reason for this is you can think of the particles within a liquid and a gas have more energy. So just as a way of talking about the phase, we'll say that solids have 1 block of phase energy, liquids have 2, gases have 3. So in this case, we're dealing with ice, so we have 1 block of phase energy. So now I've described my energy before. Now I have to think, as I put the ice on the skillet, is heat flowing into or out of my system, that is my water. And in this case, we put it on the hot skillet, so we have a higher temperature on the skillet than we have in the water. So energy is going to flow into my system. So I'm going to draw this arrow here, and I'm just shading it in so that there's not that awkward line there in the middle. So energy flows into our system. This arrow represents the heat moving from the skillet to the ice. And if you want to, you could even say down here, I can identify the object that the heat is flowing from. So it's flowing from the skillet to the water. Now, I've added energy, which means in my after situation, I have added blocks to this. And what this graph is going to be able to tell me is where that heat, because remember, once the heat energy arrives at the object, it's no longer called heat, we have to call it something else. We have to decide if that heat is going to be stored as thermal energy or phase energy. So in this case, our ice is warming up, but it's not yet melting, which means it's still going to be in the same phase. It's still going to be a solid. So my phase energy hasn't changed. It's still 1. But I did add energy here. And if I added energy, it had to go somewhere. And if it didn't go into the phase energy, it went into thermal energy. So I'll say my thermal energy has now gone up to 3. And what this shows is I can see that before I had a certain temperature and a certain phase. I added heat, and now my temperature has gone up, but my phase has stayed the same. So this graph tells this very nice story about what's going on. So this is ice warming up. And again, you won't have to label it like this. I'm just labeling it so that we have a very clear image of what we're talking about. Now I'm going to do the next situation. Let's talk about the ice melting. So I draw another lull chart. I'm still interested in the H2O. And now I'm doing this for my melting ice. Well, I can assume that once the ice is heated up, that's the situation we were talking about here. So my starting lull chart is just the one I ended with over here. That is 3 blocks of thermal energy, 1 block of phase energy. My skillet is still warmer than my water, so I still have energy flowing into my system. And that energy has to go somewhere, and so in my after chart, it's either going into the thermal energy or the phase energy. Now we said this is for ice melting. and think back about what happens to the temperature during a phase change. During a phase change, the temperature doesn't change at all. So my thermal energy has to stay the same. So all the energy that I'm adding into this from the skillet, the only place for that energy to be going is my phase energy. So now instead of 1 block of phase energy, I have 2 blocks. And notice again, this has to make sense as far as the numbers. Over here I had 4 blocks of energy. I added energy, now I have 5 blocks of energy. So it's just a matter of deciding where that energy will go. And we could do this for the rest of these situations. Once the ice melts, we have water. So we have this starting situation, and we could talk about how that is going to have more thermal energy added because it's not changing phase, and we could draw these on and on and on if you want to, as opposed to drawing a separate lull chart for each one. An acceptable compromise with that, let me switch papers here, would be to draw what could only be described as a lull chart, where you have this situation, and then you can add other graphs off to the side, or if you prefer, a lull chart, rather than do the different ones like we did here and have 2, you could take and put those back to back like this. Forgive the quick drawing here. So this is the same situation as we had before, except drawn now as one long continuous lull chart, where you can see we're doing the exact same thing we did before, only putting them together like this. If you want to do that to save space, you're more than welcome to. Remember, practice, practice, practice on this. Practicing is what's going to make you good at doing these charts. So make sure you work hard at that, and good luck.